In this paper, we propose an efficient event-based motion estimation framework for various motion models. Different from previous works, we design a progressive event-to-map alignment scheme and utilize the spatio-temporal correlations to align events. In detail, we progressively align sampled events in an event batch to the time surface map and obtain the updated motion model by minimizing a novel time surface loss. In addition, a dynamic batch size strategy is applied to adaptively adjust the batch size so that all events in the batch are consistent with the current motion model. Our framework has three advantages. A. The progressive scheme refines motion parameters iteratively, achieving accurate motion estimation. B. Within one iteration, only a small portion of events are involved in optimization, which greatly reduces the total runtime. C. The dynamic batch size strategy ensures that the constant velocity assumption always holds. Since events can be triggered by the motion of the camera, the alignment of events is highly correlated with the camera's motion. The motion estimation problem is normally cast to an optimization problem based on the alignment of events. With correct motion parameters, events triggered by the same world point can be aligned to the same pixel, forming an event frame with sharp edges. As for unaligned events, they generate blurred edges in the event frame. We construct the TS map with the backward warped events and define the pixel value at the coordinate x as follows. We propose an optimization loss of event alignment. TS loss, which is measured in terms of temporal information. The proposed TS loss is expressed as follows. We do not need to evaluate the residuals and gradients of all events, but only a tiny fraction of them are enough to provide a good optimization direction. In our algorithm, we uniformly sample a small number of events in the event batch and evaluate their TS loss. As the figure shows, the drift of the former events leads to inconsistency between the ground truth theta gt and the optimal motion parameters theta at the smallest TS loss. To fix this issue, we propose an iterative scheme to progressively update the former events in the TS map. As the iteration increases, the optimal parameters theta gt with the minimum loss value in the loss map get closer to the ground truth. In our dynamic batch strategy, we first slice the unprocessed event psi of size n into several event bundles. The event bundles that are consistent with the current motion model will be appended to the current batch. The consistency is measured in terms of the overlap ratio between the current event bundle and the previous TS map, which can be expressed as follows. If the overlap ratio of the current bundle is higher than that of the previous bundle, we append this bundle to the current event batch and fine-tune the motion model. Otherwise, we stop appending bundles and output the latest motion parameters. In Table 1, ours 30K achieves the best accuracy among all the sequences. When the scene changes or the camera resolution changes, other methods with the fixed size strategy suffer from a large drop in accuracy. Our method can dynamically adjust the batch size to adapt to these environmental changes and achieve higher accuracy. In Table 2, ours 30K shows a significant improvement and achieves a new state-of-the-art accuracy based on these three metrics. Even with 1K events involved in each iteration, ours 1K still outperforms AE-min in the translation and HDR sequences with about 18% processing time of AE-min. In Table 3, ours 30K consistently outperforms the auth-airs in all metrics. Even the real-time implementation of our 6DOF model, which involves 1K events with 3 iterations using the unidirectional warping strategy, achieves state-of-the-art accuracy with real-time processing. We integrate these velocities with their batch duration and plot the 3D trajectories. Our trajectory follows the ground truth closely and exhibits small drifts than AE-min. We present the qualitative results of the aligned event frames of different motion estimation methods in the event camera dataset. In the poster rotation sequence, these methods show relatively close alignment results. In the shapes rotation sequence, the fixed batch size of 30K events in Cmax and STPPP cannot adapt to the scene texture changes, leading to the misalignment of events. In Table 5, we present ablation studies on the rotational model with the sampling strategy, bidirectional warping strategy and dynamic batch size strategy. For the ablation of the sampling strategy, we apply different event sampling numbers in algorithm 1. This result also confirms that only a tiny fraction of them are enough to provide a good optimization direction. At the bottom of Table 5, we present ablation studies of the bidirectional warping strategy and the dynamic batch size strategy. The results of the bidirectional warping strategy are better than those of the unidirectional warping strategy in accuracy, but it comes at the cost of nearly twice the averaging processing time. As shown in Table 5. The results of the dynamic batch size strategy report higher accuracy than the fixed size strategy, especially in the shape rotation sequence. The time span of a batch with 30K events can be dozens of milliseconds so that all the events may not share the same motion parameters. In this work, we propose a unified event-based motion estimation framework for various motion models. With a novel event-to-map alignment scheme, our framework can efficiently perform motion estimations with a small number BR of sampled events. We also propose a dynamic batch size strategy to make our algorithm more generalizable to different scenes textures. Comprehensive experimental results demonstrate that our framework achieves state-of-the-art performance in terms of accuracy and efficiency. We believe that the proposed framework is a promising approach for computation-limited and time-demanding applications such as SLAM and robotics.